Last class period, we were discussing special triangles, one of them being a 45, 45, 90. Okay, so we utilized the Pythagorean Theorem and said we had this be A, this be B, and this be C. And we said, okay, Pythagorean Theorem says A squared plus B squared is equal to C squared. Then, through a geometrical argument, we were able to establish this key fact that A is equal to B, meaning that we can reduce our argument to A squared plus A squared is equal to C squared, meaning that this is 2A squared is equal to C squared, meaning we could take the square root of both sides, and this is review, but this equals that we get the square root of A, we get square root of 2A is equal to C, technically plus or minus, but we'll take the principal square root. So we get this is true.
Like, do you get a code or like, because like with the
And also, for free, by this established equation right here, if square root of 2A is equal to C, we also for free get the fact that the square root of 2B is equal to C. So we got two equations, two relations out of that. So we get C is equal to root 2B, C is equal to root 2A, and here's our third relation, A is equal to B. Now, what about the more intricate and more interesting? I would say that this would be your 60, your 30, 60, 90 situation. Here's our A, B, and C. What about in our 30, 60, 90 situation? Well, again, Pythagorean theorem states that A squared plus B squared is equal to C squared. But we cannot establish this relation that A is equal to B. Recall that all of this is for 45, 45, 90 triangles. This is for 30, 60, 90 triangles. What are we to do? How do we know the scale factors? How can we determine them?
Two times A squared equals B squared, and you just times it twice.
Say that again.
What if we just times A squared twice so it equals B?
Times A squared twice equals B. No, that's okay. That's a good attempt. The way we can solve this problem here is we have to create a mock situation in which we will scale to this triangle. So here's how we're going to do it. This is why I said it's more difficult but more interesting at the same time. What if I constructed for you a triangle that has a length 1 here, length root 3 here, and length 2 here? Would you believe me that this is true, that such a triangle exists and is possible? Yes? Why? Because it's in the book. Okay. That's okay. The answer is yes. But the reason why this is a bona fide triangle is because it satisfies the Pythagorean theorem. Notice that this is C, this is A, and this is B. So notice that C squared, which is 2 squared, it should equal B squared added to C squared. Should it not? If it does not, then it's not a triangle. So take a look. This ends up becoming 4 is equal to 3 plus 1. Check. It is indeed a triangle. What if I had some crazy situation right here and I replace this with like a 5? Would it satisfy the Pythagorean theorem? No, let me show you. C squared, which is 5 squared, is equal to B squared, root 3 squared, plus 1 squared. But this would give us 25 is equal to 3 plus 1, which is 4. Class, is 25 equal to 4? No, it's not. So, such a triangle is not a triangle. If that was equal to 5 in length, it's not possible for it to be a triangle. And the Pythagorean theorem is like a test. It verifies whether those lengths for the A, B, and C legs will indeed provide you a triangle or not. So that is why I put this as a 2. I put that as a root 3, and I put that as a 1, because it satisfies the Pythagorean theorem. So it is indeed a triangle. Why I have constructed this specific triangle, that is to be seen. We do so because we aspire to solve this in general, the 30, 60, 90 case. This triangle has 30, 60, 90 angles. So I'm going to delete this information here. We've already established it. Okay. Back to this triangle. 1, root 3, 2. What's so cool about that? Well, it satisfies the Pythagorean theorem. What's so cool about the Pythagorean theorem? Well, it allows you to test whether leg lengths do indeed give you a triangle. But within it is embedded more truth. If A squared plus B squared is always supposed to equal C squared in a triangle, then we can scale this whole equation by whatever factor that we want. Why don't we scale this equation by a factor of 1/2? Meaning I'm going to multiply both sides of the equation by 1/2. Notice that this means 1/2 A squared plus 1/2 B squared is equal to 1/2 C squared. Meaning I can scale each of these leg lengths, their squares, that is, by 1/2. And we would still retain the same value. So meaning I could scale this by 1/2 and we'd still retain the same value. Notice that if I scale 4 by 1/2, it becomes a 2. Notice if I scale 3 by 1/2, it becomes 3/2. And if I scale 1 by 1/2, it becomes 1/2. It still establishes equality because this is 2 is equal to 4 over 2, which is 2. This is a proof as to why I can say that this is equal to 1, this is equal to root 3 over 2, and this is equal to 1/2. Notice that the scale factor is also present. Notice we got this and we scaled it by multiplying this by 1/2 to turn it to 1/2, this by 1/2 to turn it to 1, this by 1/2 to turn it to root 3 over 2. Notice that this also adheres to the Pythagorean theorem, this triangle. Why? Because 1 squared equals 1/2 squared plus √3 over 2 squared. Notice this implies that 1 is equal to 1 over 4 plus 0 over 4, which is equal to 4 over 4, which is equal to 1. Cha-chink. Okay? So, if I could scale this triangle by multiplying all the legs by 1/2, and it still remains a triangle, that means I can multiply this triangle by any value. Call it x, call it x, call it x. And when we scale it by x, it still adheres to the Pythagorean theorem. And thus, we have found the special rule for 30, 60, 90 triangles. Here's a special rule for these guys. We already established a special rule that works for all 45, 45, 90 triangles. Here's a special rule that works for all 30, 60, 90 triangles. It's that, oh, I deleted it. I deleted it. Recall that this was a √3, this was a 2, and this was a 1. And so when we scaled it, this was the fact that was true. A is equal to 1 times x. B is equal to √3 times x. C is equal to 2 times x. So we have the following transformations. C is equal to 2x. B is equal to √3x. And A is equal to x. Your book has A instead of X. So on page 5, for the 30, 60, 90, if you have your books open, if not, it's okay. They have, instead of X, they have an A. All right? Because notice that A is X. 1 times X is X. So A is equal to X. So this equivalently can be represented like this. You can just say A is just A or X. Okay. So why is this even important? Why does this even matter? Well, one thing that's important about these equations is that they apply to all 30, 60, 90 triangles. That's very important. Anytime you see a 30, 60, 90 triangle, these equations can activate. All right. Furthermore, these allow you to only be given one length, the A, and to be able to determine the hypotenuse and the other leg, C and B. So that's another reason why they're important, is because all you need is to be given the 30, 60, 90 triangle and to measure what the leg A is. Once you measure it, you can determine C and B utilizing these equations. That's what's cool about it. That they work for all 30, 60, 90 triangles. And that you only need 2 pieces of measurement. I know what you're thinking. Well, you know, what is that going to do for me? Well, it does a lot. Let's say if you're an engineer and you're building a huge bridge, and this is the bridge and this is the cables attached to it. You don't want to have to go out there and measure all of that. You can know that if I form a 30, 60, 90 triangle, and I know how long my bridge I want it to be, then, or how high I want it to be, if you will, then I can figure out how long it needs to be and how long the cable needs to be to attach it to the beam, if you will. It's very, very practical in real life. Us mathematicians don't care about real life. but it just so happens that sometimes the abstract concepts that we invent correlate to real life and that they are useful. You can imagine that, you know, here's a river, bridge over the river. You see that? All right. So that's that. Let's do some examples where we apply these equations so you can see why that they're even a thing. So let's say you're given a 30, 60, 90 triangle and you know two things about it. So you're given a 30, 60, 90 triangle and you know two pieces of information, A and B. You know that the hypotenuse is equal to 10 meters. And you know that the longer leg measures 4 square root of 3 inches. So we typically let the longer leg be B. All right. So this problem is going to have a 30, 60, 90 triangle. Here's our 30. Here's our 60. Here's our 90. Here's our hypotenuse, C, which is 10 meters. Here's our shorter leg, 4 root 3, or B. This is in inches, that's in meters. Oh my. Oh, I'm mixing these up. I have two triangles here. Let's do this one by one. There we go. No wonder. They don't want you to convert between units. So here's triangle A. Here's triangle B, and we'll solve them separately. Both 30, 60, 90 triangles. Shorter leg here, B, is equal to 4 root 3 inches. Okay. We erased it, but our 30, 60, 90 rules, what were they? They said C was equal to 2A, didn't they? They said B is equal to root 3A, didn't they? Right? Yeah. So let's take this equation. Which one of these algebraic variables, C or A, are we given in the problem? Yes. So let's replace C with that numerical value that's given, 10 meters. So notice now that we've replaced it, we can solve for A by doing what to both sides? Yeah. This implies that 5 meters is the numerical value for the leg A. All that's left to remain is to find the numerical value for the leg B. How do we find that? This equation. Say what? Plug in 5 for A. Excellent. So notice that this implies that B is equal to the square root of 3 times your A, which is 5. This equals square root of 3 times 5, which is your B. Square root of 3 times 5. Done. Given just one piece of information about a 30, 60, 90 triangle, you were able to extract these two pieces of information. That's what's cool, because when you have this mathematics, it saves you time. You don't have to go measure this, and then measure this, and then measure this. you can just measure this, know it's a 30, 60, 90 triangle, and mathematically solve for the rest. In real life problems, this saves you a lot of time and energy. That's why it's critical. Now let's do this problem. B is given by 4 square root of 3 inches. C is an unknown, and B is an unknown. How do we figure it out? We know it's a 30, 60, 90 triangle. So we know that it adheres to these rules, that C is equal to 2A, B is equal to the square root of 3A, and A is A. So how can I find I have those labeled right? The longer leg, yes. Good. Okay. So what is A? We know what B is here, right? So we replace it with the 4 square root of 3 because we know what B is. This equation has B is equal to root 3A. We are given what B is numerically. We'll replace it with the numerical given information. Next, we can discover the numerical value for A by doing what to both sides? Say what? Divide by square root of 3. They cancel here. They cancel here. So that implies that A is equal to what? Excellent. So you get A numerically is equal to 4. What about C? At this point, you could use the Pythagorean theorem to solve for C, couldn't you? Because you have 2 legs, and you can solve for unknown. But you can also utilize this equation right here. That C is twice your A. And that's a lot easier than taking square roots. So this implies that C is twice your A that you discovered to be 4. Which implies C is equal to what? 8. Well, there you go. And don't forget that these are in inches. The unit that we're working in is inches. And don't forget that these were meters, because the unit that we were working with are in meters. Make sense?
Question.
Yes, sir.
For example, if we had a question and we only were giving the 8 inches, can we just divide? And if it was a 30, 60, 90 triangle, can we just divide 8 by 2? Then we get the.
Let's do it. To honor your question, we will do that very problem. Here's C, here's B, we don't know it. Here's A, we don't know it. But we do know, like you said, it's a 30, 60, 90 triangle. So C is equal to 2A is true, and B is equal to square root of 3A is true. These equations hold, don't they? You can replace that with what?
With A.
Is equal to 2A, right? So what is A when you divide both sides by 2? Yes. So this becomes a 4. Right. Then what about B? It's just square root of 3 times your A, right? So B is equal to the square root of 3 times what we've discovered for A, which is a 4. So this becomes 4 square root of 3. I'm very happy that you asked this question because it allows us to exemplify that you can derive the same results given a combinatorial mixture of information. Right? You could have been given the hypotenuse and had to discover the A and B. Or you could have been given the B and had to discover the A and the C. Or you could have been given the A and had to discover the B and the C. Yes, ma'am.
On the one we just did, y is b equals 4 square root 3, and then on the first one it was b equals square root 3 times 5. Like when we did that part, like on the first one for b,
Oh, this is a different problem.
Okay.
This is a different problem than this one.
Okay. I'm asking about the middle one.
This one.
Yeah.
These two problems right here are the same situation.
Okay.
That's why they're having the same results. They're the same 30, 60, 90 triangle, except in this version, you were given C and you discovered B and A after that. In this situation, you were given B and then you discovered A and C after that. Does that make sense?
Mhm.
Yeah, that's the difference. Okay. So let's apply this to a real life situation. Let's say we're on a boat in the ocean. Here's the ocean. Here's our boat. And let's say attached is some type of kite. It looks like an ice cream cone or something. All right. Let's say that we can create a right triangle out of this situation. So that this is at 45 degrees exactly. That's at 90 degrees. And what do you think that last one has to be at? Yes. Why? Yes. If this is question mark angle, and the sum of the interior angles have to add up to be 180. And you algebraically solve for question mark, right? Subtract by 45, subtract by 90. You get that 45 degrees is equivalent to question mark. So that's indeed, as you suggested, 45 degrees. That's the reason why. Okay. So let's say you have this kind of a situation. We're on a boat. Attached to our boat is some like kite or some parasail or whatever. Let's say that we know how long the cable extends. It's our cable, it's our boat. We bought the cable from the store and it says that this cable measures 216 meters in length. But we're interested in finding this H. How high is the parasail off of the ship's floor in height? How do we figure out what H is? We really want to know what is H.
So we just use the A squared plus B squared equals C squared.
That works. That is a true statement that A squared plus B squared is equal to C squared. However,
You can use A equals B.
we're going to get to that. Why is it that this, although it's true, is not useful in this situation? That's what I want to know. Say what? There's no A or B.
We are listening to all of them.
We just have a C, right?
Mhm.
For the Pythagorean theorem to work, we need to have 2 out of the 3 letters known, right? If we knew how much this was, we could have used the Pythagorean theorem to solve for H, but we don't. We only have a C. We know C is equal to 216 meters, but we don't know what A is, and we don't know what B is, where B is the same thing as H. And this is A. We don't know what B or A R. We're really looking for B, which is your H. So the Pythagorean theorem, although it is a true statement, it does not apply to this problem. It can't help us solve the problem. Who has another idea? Yes. For the what kind of triangle? Yes. And what do those equations establish? The what? A is equal to the square root of, wait, what did you say? Did you say A is equal to the square root of 2A? C is equal to the square root of 2A? Okay. And thus, because A is equal to B, this is true, right? Because this is true. These three equations are true. This would mean that A and H are equivalent. In our situation, this implies that A is equal to H, which is what we want to find. Our C, we already know. This one right here, we already know. We know what C is, don't we? Yes. So we can find A, which in turn finds B, which in turn is H. By doing what? Yes. So A, which is the same thing as H, is 216 divided by square root of 2. Whenever you plug that into your calculator, what do you get? Approximately 152.7 meters. So we know what the height is, 152.7 meters. Isn't that cool? Isn't math cool? It really is, because you didn't have to jump into the ocean. There might be icebergs around, even though I'm into that. I'm into swimming in ice cold water. But you don't have to swim out there with the measuring tape to see how much this is to be able to do the Pythagorean theorem, right? If we only had the Pythagorean theorem, if it was me, I'd have to jump out of that ocean and swim. I'd do it just for the fun and the exercise and the cold training. But it'd be nice to be able to calculate it real quickly, right? Let's say you weren't on the ship with me. Not everybody likes ice cold water. So, furthermore, there's sharks. Yeah. So that's 1.1. Moving on to 1.2. Triangle classifications. We already talked about right triangles, our 30, 60, 90, and our 45, 45, 90. There are right triangles. Right triangles are triangles that have 90-degree angles in them. So we call them a right triangle. Now, we also have triangles called acute triangles. They're triangles such that all of their angles, alpha, beta, theta, less than 90. There's an obtuse triangle. Where one of the angles, let's call it alpha, theta, and beta. Alpha is greater than 90, and theta and beta will be less than 90. So an obtuse triangle has one obtuse angle. An acute triangle has 3 acute angles. A right triangle has one 90-degree angle. What kind of a triangle is this? Close. We're going to get to isosceles in a second. Very close.
Equilateral.
Equilateral. So isosceles is like this. Right? I don't even know how you spell that. Isosceles. Where 2 leg lengths are the same, but one is different. Whereas equilateral, they're all the same. And there's 2 L's. Nope, got that one right. What about a triangle like so? What kind of a triangle is this? Where all the leg lengths are different lengths. Scalene. This is called a scalene. This is isosceles. This is equilateral. You know what? This stuff really isn't anything but trying to give names to different species of triangles. Okay? We want to be able to differentiate the different kinds of triangles that we'll ever encounter. And so we'll give them some names to make this one distinct from the other one. So, notice that this is a scalene right triangle. But we can have a non-right scalene triangle, right? This is scalene, but it's not right. This is scalene and right. That's isosceles. This is equilateral. Okay. So here's some properties of triangles that we've already touched upon. One is that, at least in flat Euclidean geometry, that the sum of the interior angles is equal to 180 degrees. What do I mean by at least in flat Euclidean geometry? Well, I mean, if you only draw your triangles on flat sheets of paper or flat surfaces like this board, then yes, the sum of the interior angles will equal 180 degrees. Like so. Right? This is one of those triangles where this would be true. However, this is in flat geometry. There's curved space. There can be positively curved space and negatively curved space. What are the examples of that? Well, we can form a triangle. Here's your alpha, beta, here's your theta. Equals 180 degrees. But what if we had a triangle like so? What do you think alpha plus beta plus theta equals here?
180.
No, greater than 180. Maybe 360. Maybe. But let's just say that it's just greater than 180. This is in positively curved space. Here's a triangle in negatively curved space. Where alpha plus beta plus theta, what do you think here? Yes. So the mathematics we're going to be sticking to is in flat space, where the sum of the interior angles does equal 180 degrees. However, these kinds of geometries do exist, and mathematicians do study them. Matter of fact, near the region of infinite space and time curvature, near a black hole, space-time geometry is no longer flat and Euclidean like so. It actually curves like this and curves like that, depending on whether the gravitational wave is at a peak or a trough. Space and time can actually be positively curved or negatively curved, affecting geometry and relativistic effects. None of that will be on your test, though. No need to worry. So this is property 1. Here's property 2, that alpha plus beta is always greater than theta. Alpha plus theta is always greater than beta. And beta plus theta is always greater than alpha. Oh, what am I doing? Those are for the angles, right? Let's create a triangle. Here's beta, here's alpha, here's theta. What I mean here is not an angular statement. Here's A, here's B, here's C. It's a length statement. It says that A plus B is always greater than C. It says that B plus C is always greater than A. And it says that C plus A is always greater than B. Our last statement is one of the statements that we utilized to prove the 30-60-90 rule and the 45-45-90 rule, is that the larger angles are opposite to larger sides. So let's call this angle little c, capital C, angle little b, capital B, capital A, little a. So the angles are now A, B, and C corresponding to the opposite leg length, capital A, capital B, capital C. So it says that, okay, if your angle C, little c, is greater than your angle, let's say little b, that implies that the leg length C is actually greater than the leg length B. Larger angles have corresponding larger opposite side lengths. Makes sense, doesn't it? The larger this angle, the larger the leg. The shorter the angle, the shorter the leg. These are our 3 basic properties of Euclidean triangles, not non-Euclidean triangles. If you want to learn more about non-Euclidean triangles, well, you're going to have to take differential geometry with me, and then Einstein's theory of general relativity. Take more math. I want all of you guys to turn into math majors. Now that I said that, let's take a real quick break to interview you guys, and you guys tell me what your majors are. What's your major? Your name and your major.
Kelly.
Callie? Kelly. Computer science, okay.
Maya, biology, chemistry.
Maya, biochem.
I'm Ashley, I'm biochem.
Ashley, biochem.
Marcus, network engineering.
Marcus, network engineering.
Robinson, software engineering.
Robinson, software engineering, basically computer science. And
Muhammad, computer science.
Mohammed, computer science. Okay. Yeah, all of you guys switch to math. Math. Just become math majors. Or if you know, double major. Do it. No? Oh, okay. Well,
I'm terrible, no. Never.
well, it was worth a shot. Maybe you think that now, but at the end of the semester, you might change your tune. Who knows? Okay. So now let's move on to another situation where we're given an unknown triangle and we hope to find some information about it. Let's say we're given these angles here, and this is A, B, and C. 2 alpha, 4 alpha, 6 alpha. What is alpha? So in order to avoid confusion, here's a problem. You're given a triangle here. We're asked to find what is the value of alpha. How can we find that value? Which one of these properties might be useful? Oh, what was that? Property number 1? Yes. Say what? You're about to say it too, huh? Well, I could read. When you become a mathematician, you could read people's thoughts. Now, we don't tell people that unless we're trying to recruit them. Property number 1 would suggest that 180 degrees will be equivalent to adding 2 alpha to 4 alpha to 6 alpha. Would it not? But this doesn't help us find alpha. We don't know alpha directly from this. But what do we know? What do we know? What do we know?
You can add them all together and divide it by
Just divide by 3.
12.
12. 12 what?
12 alpha.
12 alpha? Are you saying that if this is 2 alpha, 4 alpha, 6 alpha, it's like saying I have 2 oranges, 4 oranges, 6 oranges. How many oranges do I have? 12 oranges. You see, people typically don't like math because they don't get it taught well. And we don't get something taught well to you, you find it frustrating because it doesn't make sense. When you find it frustrating and it doesn't make sense, especially if you're a little kid being forced to do it, then you don't have a good feeling about it at all. The thought of it makes you want to vomit. It's a process called classical conditioning. Who here knows what about classical conditioning is?
I know what it is, but I don't remember.
Well, can you explain what classical conditioning is?
I'm not sure.
You've heard of it before, right?
Yeah.
What was the situation involved with it?
Like learning of early psychology, so like learning of a child, some trying to think.
Remember the dogs? Pavlov's dogs? So there was this scientist, Russian scientist named Pavlov.
Was it monkeys?
It was dogs. He had some dogs, and every time he fed his dogs a big chunk of meat, ding,
Oh yeah.
he'd play one specific note. You remember, huh? Bing, every time you feed the dogs bing, you give that no. So that they associated bing with the food time. So actually, Pavlov decided to go bing with no food present at all. What happened to the dogs is they still started to salivate because they associated the sound bing to food time. Whenever you don't get taught math properly and you associate bing, math with frustration, annoyance, anger, feelings of inadequacy, feelings of everything negative, of course you're not going to think of math in a positive light. I too was in the same shoes as yours. Math was my least favorite subject growing up and worst performing subject growing up until I started to connect the dots, and it helped to have some good teachers. I had a few good teachers that helped me connect those dots. And then I really liked math. Went on to do theoretical nuclear physics research for the United States government and want to become a mathematician. So I started out at SMU Biochem and slowly started to take more and more math and physics courses. So maybe you guys might turn into mathematicians as well. Who knows? So how we find alpha? So 12 can go into 180 how many times? $15 times, right? Because 12 times 15 is 180. Right? Another thing, math is not being able to multiply and divide numbers in your head really fast. That's not what math is. That's arithmetic. Growing up, I thought that that's what math was, and I didn't like math. Who cares what 136 times 5,341 is? Who cares if you can do it really fast? I mean, of course, you can impress people at parties, but besides that, you know, being a human calculator is not necessarily that cool. It's these mathematical associations and these concepts that are cool. So if a computer can do it, if a device can do it, it's not that impressive. Although with artificial intelligence, what computers and devices can do is being more and more impressive. I doubt that they can be as impressive as me or as you if you're a mathematician. So now that we know what alpha is, it's 15 degrees, what is angle little a, angle little b, angle little c? What do they equal? 2 times 15, which is 30. 4 times 15, which is 6 times 15, which is 120. 120. Notice that if that was 120, 30 plus 60 is 90. 90 plus 120 would exceed 180 degrees, right? Oh, it's a 90. Now, when could it be 120? As if you were in higher curvature. If you were in one of those non-Euclidean triangles, you could get something like that happening. Some of the interior angles could actually exceed 180 degrees. But because we are arrested in Euclidean geometry, we will have to adhere to having the sum of our interior angles equaling 180 degrees. No more, no less. If you have anything deviating from that, then you don't have a triangle in flat space. What if you're given 3 sides and 2 angles of a triangle? One, 5, 6 centimeters. Hey, you know what? We don't really need to put the units. 131 centimeters. And 147 centimeters. And let's say that they have these associated angles here. (51 and 61). Degrees. What is this value? Theta. And how can we find it? Say what?
68.
68. How do you come up with such a number?
61 plus 51 equals 1. Divide minus 180.
Ah, so you're saying utilize property number 1. This is alpha plus beta plus theta should equal 180 degrees. Then you're saying that means 61 plus 51 plus this unknown theta should equal 180 degrees. Therefore, theta, algebraically solving, is 180 minus 61 minus 51.
112.
Say what?
It's negative 112, 61. Negative 51 plus negative 61 is negative 112.
Okay, so then when we subtract it from 180, we get?
68.
Does this answer make sense? If we add 68 to 51 and 61, what number do we get? 180. So yes, the answer does make sense, right? This was me tying it to the triangle property. If you wanted to, you could have just jumped to this step right here. But just know that you're jumping to that step because of this property. Most people just jump to this step and get this answer. What you don't know is that it's this property that's leading you there. Okay, make sure you take a note and say thank you, property 1. Now that we've done that, let's talk about similar triangles. Who can tell me what a similar triangle is?
They will same.
They're the same. So if the triangles are literally the same, those are called congruent triangles. So like this triangle and that triangle, they're literally the same. All I have to do is pick this up and put it on there and they overlap perfectly. Those are called congruent triangles. They're not similar triangles. So what is a similar triangle? Notice a congruent triangle has angles all the same and leg lengths all the same, right?
Are they like the same like shape but different sizes?
Yes. More specifically, similar triangles are triangles that have the same interior angle values but different leg lengths. So for example, this and this. This is, let's say, a 30, 60, 90. But so is this. But why do they look so different? Yeah, this is a scaled up version of this. Each leg length has been scaled up. And you know how to scale those up in a 30, 60, 90 triangle, right? Remember? C was equal to 2a. B was equal to square root of 3a. And a is just a. So a similar triangle is a triangle like so. Let's say we have a triangle like this. A similar triangle to it could just fit right in there. I'm using the 30, 60, 90 example. It doesn't have to be a 30, 60, 90. It could be any kind of triangle, as long as they have the same angles, but different leg lengths. Notice that this has 30, 60, 90. This bigger one, the white triangle, has 30, 60, 90. Make sense? So similar triangles are triangles that share the same angle values, but not necessarily the same length values. Let's solve a problem, okay, using similar triangles. Let's say we've got a person here, and they cast a shadow. There's a sun, and they cast a shadow. Okay. We can create a triangle given the person's height, the shadow length. All right. Then let's say identical situation. Got the sun, got the flagpole. It also casts a shadow. And guess what? You can create a triangle out of this situation as well. Specifically, a right triangle. Out of both situations, we can create a right triangle. Okay? Let's say it is known that this person is 5 feet 6 inches. Okay? And let's say her shadow, when we go out and we measure it, is 8 feet. Notice that her triangle and the flagpole triangle are similar. Why is that? Because I can take this and embed it right here. Where we know this length right here is 8 feet, and this length right here is 5 feet 6 inches. What we aspire to find is how tall is the flagpole, this H. We are also go out and use a measuring device and calculate that the flagpole casts a shadow of 44 inches. This is why math is cool. You don't need someone to go climb up that flagpole with a measuring device. You could just use mathematics. So how are we to solve this problem for H, knowing that the triangles are similar? Well, I haven't told you the most characterizing property of a similar triangle. And that is this. If two triangles are similar, let's say we have this triangle, and let's say we have this triangle. The orange and the white triangle. Okay. If this is A, B, and C, and this is capital A, capital B, capital C, we note that the side lengths are proportional. What does that mean? Well, it means if I take the ratio A over B, it should be equivalent to the ratio capital A over capital B. If I take the ratio B over A, it should be the same thing as the ratio capital B over capital A. If I take the ratio C over A, it should be little c. It should be the same thing as capital C over capital A. And any kind of combination you can find. This is what triangle similarity gives you. So, applying that situation to our shadow problem, what do we get? Well, we can set up what those things are called. They're called proportions. Those ratios being equivalent to each other, those are called proportions. So we can set up a proportion. We can say that this 5, 6, which is this, divided by this 8, is the same thing as this unknown h, which we want to find, divided by this known 44 inches, or 44 feet. How do we find h? Simply just multiply both sides by 44 feet. They cancel here. And then you get a is equal to 44 feet times 5 feet 6 inches divided by 8 feet. Okay. So the height ends up equaling, when you do the appropriate conversions, is you get 30.25 feet. No, in order to do that calculation, you will need to convert 5 feet 6 inches into all feet, right? So notice that 5 feet 6 inches is the same thing as 5 feet plus, if we want it to be completely in feet, we got 6 inches times, in 1 foot, how many inches do you have? 12. So the inches cancel. So 12 goes into 6 half a time. So this becomes 5.5 feet. So we could have replaced this with 5.5, and our answer would be in feet. And this is what we get here. So replace this with 5.5 in your calculator when you do the computation, because you want all your units to be in the same unit, feet, not feet mixed with inches. Okay. Let's find the unknown sides of similar triangles. Let's say you have a triangle like so. And let's say you have a triangle like so. where the thetas are the same. First of all, are these triangles similar? Yes or no?
They both have right angles.
Why are they similar?
Because they both have right angles. And they both have theta.
That means that last angle is what?
The same.
That means this last angle is the same as this angle. So recall, similar triangles were triangles that had all the same angles, but possibly different side lengths. So this means that they are indeed similar. So why don't I kind of orient this one to look kind of like that one? Meaning, let me just like reorient this guy right here. Put a theta here. Put a right triangle here. Opposite of the right triangle is that 3x. Opposite of the theta is that 6. Opposite of that undesignated angle is no value. So now we flip that similar triangle to be in the same kind of orientation as this other one. Now it all kind of makes sense. What we want to know is, what are all the leg lengths? So what is this equal to? And what is this A equal to? And what is this equal to? In order to solve this system, which algebraic variable do we need to solve for? Say what? X. We want to find X. How do we find X? Because this is not necessarily a 30, 60, 90. This theta can be anything. It's not necessarily a 30, 60, 90. Furthermore, it's not necessarily a 45, 45, 90. So what are we to do?
Can we set up a proportion?
Yes. What is the proportion you want to set up?
C equal to A or C over the smaller A.
Should equal what?
Capital C, capital A.
Very good. Very, very good. Yes. So the C in one of them divided by the A in that one. We do it like that. Signify the orange and the white triangles. So C in this case is your 6. And your A in this case, we don't want to use A because we don't know it. And we don't want to use capital A because we don't know it either. So how about we switch to B, capital B, right? Does that make sense while we're switching?
Yeah.
Make this little b, make this capital B, because we don't know the A, they're unknown. We do know the B. Furthermore, the B has the X in it that we aspire to find. So C, capital or lowercase c becomes a 6. Divided by lowercase b is just x plus 1. This is equivalent to your capital C divided by your capital B. Okay. Now we just do some algebra. If we multiply both sides by 6, cancels here and it multiplies times there. So you get 36 over x plus 1 is equal to 3x. Then we multiply both sides by x plus 1. This implies we get 3x times the quantity x plus 1 is equal to 36. Distribute that 3x to each of these. You get 3x squared plus 3x is equal to 36. Subtract the 36. 3x squared plus 3x minus 36 is equal to 0. Now we have a quadratic equation that we can solve for the variable x. Right? So in order to solve this quadratic equation, it would be simpler to factor out a 3. Factor out a 3, I get x squared. But before I do that, I want to show what's going on. 3x squared plus 3x minus, what's 36? It's really 6 times 6. But 6 times 6 is the same thing as 2 times 3 times 2 times 3. So when I factor out a 3, all that remains is the 2, 2, and 3. So then when I factor out a 3, I get 3 times x squared plus x minus a 2 times 3 times 2. It doesn't have that additional 3. Now I can divide both sides by 3. Cancel. 3 goes into 0 no times, so it becomes a 0 over here. So this becomes x squared plus x minus 2 times 2 is 4, times 3 is 12. So you get x squared plus x minus 12 is equal to 0. This is a quadratic equation that we can solve for. So then bringing the calculation over here, we can factor it. Two numbers that multiply to give me a negative 12, but add to give me a positive 1. 4 and what? 4 and 3. Which one's positive? Which one's negative? 4 is positive, 3 is negative. All right, this factors to this. So we can separately set each equal to 0. And we can solve. So that means x is equal to negative 4, x is equal to positive 3. These are our possible solutions for x. But notice, if we were to pick x is equal to negative 4, this value would be a negative value. Negative 4 plus 1 is a negative 3. We'd have a negative leg. Notice that 3 times negative 4 would be negative 12. We'd have a negative leg. In order to retain positive leg values, we will throw away this value and retain the meaningful value, x equals 3, because we don't want negative lengths. So that means b is equal to 3 plus 1, which is 4. And c is equal to 3 times 3, which is 9. Okay, so now we know b and c. We can solve for a using the Pythagorean theorem. So 6 squared is equal to unknown a squared plus our known 4 squared, which is b. So 36 is equal to a squared plus 16. So a squared is equal to 36 minus 16, which is equal to 20. Which means a is equal to the square root of 20. This decomposes to 2 times 10, which is equal to 2 times 2 times 5, which is equal to 2 squared times 5, which is equal to 2 square root of 5. That's your a. And then for capital A, we utilize the Pythagorean theorem again. We say that 9 squared, which is our hypotenuse, is equal to our unknown capital A squared plus our known 6 squared, which is our b, capital B. So this gives me 81 is equal to capital A squared plus 36. So then I get A squared is equal to 81 minus 36. So A is equal to the square root of, what's 81 minus 36? Can't do it in my head. 45. So A is equal to square root of 45. 45 is 9 times 5. Right? So 9 is really 3 squared. So when I distribute the radical, I get 3 root 5. So A is equal to 3 root 5. And this A is equal to 2 root 5. We found that earlier. Class is dismissed. We actually ran like 6 minutes over. 7 minutes now. I'll try not to do that very often.